Today we are going to see likelihood function and its property. So what is a likelihood function? Definition of likelihood function is given by if x1, x2, xn be a random sample from family of distribution fx theta, then likelihood function of theta for given x1, x2, xn is nothing but joint distribution of x1, x2, xn. So joint distribution of x1, x2, xn is product of fxi theta or product of pxi theta. If xi is continuous, then this is product of fxi theta, and if xi is discrete, then it is product of pxi theta. Here we are writing joint distribution as product of their marginals because x1, x2, xn are independent, that is they are random samples, so they are independent. So we will now see some of the properties of likelihood function. To learn about properties, we have to see some Cramer regularity conditions. We have to see these conditions because under these conditions we are proving the properties of likelihood function. So first regularity condition is x1, x2, xn is a random sample and xi is random variable from distribution fxi theta, and fxi theta is a PDF. This is first condition. Second condition is that parameter space is subset or interval of real line. Subset or interval of real line. Our next condition is x1 range of xi. A range of xi should be independent of theta. That is, range of xi should not depend on theta. Our next condition is that dou by dou theta of product of integration of product of fxi theta can be written as integration of dou by dou theta of product of fxi theta. So here integration and derivative are interchangeable. Our next property is if t is an estimator of theta, then we can write dou by dou theta of integration of t into product of fxi theta, integration of t into dou by dou theta of product of fxi theta, where t is an estimator of theta. So these are interchangeable. And the next condition is that dou log f by dou theta exists for all theta. All theta belongs to parameter space. So this is our next sixth condition. And seventh condition is that expected value of dou log f by dou theta square should be finite. It should not be infinite. These are the conditions, 7 conditions of Cramer regularity condition. Now, by using these conditions, we are proving properties, 3 properties of likelihood function. The first property is that integration of likelihood function is equal to 1. And this is obvious because likelihood function is nothing but a joint distribution function. So this integration is equal to 1. This is first condition. Now we will prove expected value of dou log L by dou theta is equal to 0. Now we have this, that is integration of likelihood function is 1. So dx1 dxn is equal to 1. Now differentiating both sides with respect to theta. So integration of dou log L by dou theta of dx1 dxn is equal to 0. Now due to the Cramer regularity condition, derivative comes under integration. These are interchangeable. Now we will multiply by L and divide by L. So L into 1 upon L dou log L by dou theta into dx1 dxn is equal to 0. So integration of L into, this is nothing but this is dou log L by dou theta, not dou log L. So it is dou log L by dou theta, and 1 upon L dou log L dou L by dou theta can be written as dou log L by dou theta dx1 dxn is equal to 0. So L is a something like a PDF. Its integration is 1. So this is nothing but expected value of dou log L by dou theta, and this is equal to 0. So this is a proof of this second property. Now we will prove expected value of dou log L by dou theta bracket square can be written as minus expectation of dou log L by dou theta square. To prove this, we will use previous result. We know that expected value of dou log L by dou theta is equal to 0. So that is integration of L into dou log L by dou theta dx1 dxn is equal to 0. Now we will differentiate this function with respect to theta. So dou log L, dou L by dou theta into dou log L by dou theta dx1 dxn plus integration of L into dou 2 log L by dou theta square dx1 dxn is equal to 0. So now we will multiply here by L and divide by L. So what we have, integration of L into 1 upon L dou L by dou theta into dou log L by dou theta dx1 dxn. Take this term to the right side, so which is equal to minus of integration of dou 2 log L by dou theta square into L into dx1 dxn. So what we have, L into, this is a dou log L by dou theta, and this is also dou log L by dou theta dx1 dxn, and minus of minus sign, and this is nothing but expectation of dou 2 log L by dou theta square. So this is nothing but integration of L into dou log L by dou theta square dx1 dxn is equal to minus of dou 2 log L by dou theta square, and this is nothing but expected value of dou log L by dou theta square is equal to minus of expectation of dou 2 log L by dou theta square. So this is a last property of a likelihood function, and we will now stop here. Thank you.